Hey all, I've seen this discussion about normalization and the question that Ognian placed it, and I would like to respond. And it's easier for me just to create this little video with animation because then I can do something here. Um, in fact, a quick answer is the animation we are producing was just to give us a sense of, or in fact, to the students and to all of us, the sense that we can really uncover a lot of good science out there, even if we are not responsible for submitting observing proposals. We sometimes groups they submit requests to observations because they want to study a specific feature in a certain specific wavelength band, and our project is one that required coverage, as much coverage as we can, spectral coverage, and we use the advantage of time series. So we don't have time series in TW, except that if we think about observations done, few of them per month in a year, we might, okay, we have also time series, but with a long time span between observations. So I think we have a really, really good set of data points. And if we can, again, develop the tools and the techniques, and we are comfortable with analysis, we can quickly switch this and apply this routines, these applications the boys are developing to quickly study other stars and even studying the same stars, TW or RU or GQ, but observed with different types of spectrographs, with different resolutions, with different CCDs, or you know. But anyway, so let's go to the point of normalization. It's not a big issue, and the quick answer to the question is right now, don't worry about it. It's not a big issue. I knew usually when we see emission lines, we tend to put our mindset in assuming a continuum normalized, oops, sorry, a continuum normalized at 1.0, which means if you have a spectra out there you observed, right? Let's say you have a spectra and you have some absorption line, and then a little bit further you have some nice emission line, and then that thing goes like that. And we wanna, and this is the boys are going to do that. It's a lot of work. What we want to do, let's say this flux is given. This is wavelength in angstroms, let's say, and the flux here. Let me erase this. And the flux here is in units of ergs per centimeter square per second, and per wavelength. Let's say we have a per angstrom, right? So we have a flux given that way, and let's say if this is given in units of flux, right? So times 10 to minus 13. So then we have something like 8.5, 9, 9.5. I'm just inventing data here. 10, 10.5, and so on, so on, so on. So you let's say we observed the flux and or the star, and we were able to calibrate in flux, and these are wavelengths, and this is a continuum. The continuum is about 9.5, 10 to minus 13 ergs per centimeter square per second per angstrom, so on, so on, so on. Okay, good. Now, when we present tables and when we present profiles in publications, usually we present the profiles like this with the real flux measured at the detector, right? Or flux we receive here on Earth. Uh, so that's one way of presenting. But um, we don't have that. We don't have this flux calibrated that way. We don't have calibration, right? So what Ferrous pipeline data reduction pipeline does is to do the reduction and then put everyone in a weird normalization. And if you go to their normalization, so this is the wavelength in angstrom. So this is zero flux, and this is 1, and this is 2, and then it goes 3, 4. Now, the continuum, which should be these points over here, right? It's called continuum. This is a line, and this is continuum. Continuum, the flux in continuum is formed by all kind of processes that involve transitions between excited levels and the continuum. Is also the result of scattering um, or interactions of radiation with electrons, ions, hydrogen, negative hydrogen, all kind of things, and then it creates this continuum. But a specific transition creates lines, right? So we have two different things: lines and continuum. Continuum is in a small spectral window should be relatively flat. Okay. Now, what Ferrous do, the data reduction, is to put this continuum level not at 1, but somewhere pretty much close to 0, right? 0.1 maybe. I don't remember, but it's a crazily small number. So when you look at the spectra, you have this kind of a flatten, so the emission here becomes something that's almost nothing because it's all collapsed. That's why when you just read the FITS file and you plot, you have this almost nothing line appearing, right? There is almost nothing there. And then towards the edge you have this junk, which is pretty much noise or vignette. I don't know, it's some artifact of the data reduction, I think. So what we want to do is to take this spectra, and then I say, okay, if you just want to have a quick look, divide by the mean or median of the whole thing, the whole enchilada. It's because when you do that, the spectra will appear. Let's see, like this. Lambda angstrom. So this is 0, right? And this is 1, 2. So the spectra will appear like this, like the one on the top, kind of a close to 1, right? And then you have your emission line, and then you go there, pretty much close to 1. So the continuum, the shape of the continuum is the same as it is here, right? Because you're just multiplying every one by a factor. So then they by a factor that is less than 1, and that's why it raises to 1 level, and then you can see the lines, the profiles better presented. Okay. Now, so when we divide by the average, what you do, you raise every continuum, or you raise the continuum to a number close to 1. Okay, so that's what I did, and that's what Shaunak did. I think Philip did, and it really what we did was just for fun. We are not presenting data that way. So how we are going to present data? You know this animation we did with the H alpha? If we want to do something like that at the level of showing in a presentation, or what you need to do is to go to first of all, you have to have a sense of organization that is worse than my wife, I would think. You have to be able to really organize and create your subdirectories or subfolders in such an organized way, otherwise it becomes a big confusion. So what you do, you have to take the raw H alpha, let's say, you have a fits file 1. So we have 92 for TW, we have 92 files, right? Which means we have 92 H alpha. So what we need to do is to take and define, and I haven't gone there yet, but we have to go, let's say this is H alpha. We have to go and determine where exactly at which wavelength the H alpha shoulder ends. You know what I mean? Because H alpha is a heck of a line. And this line sometimes, without we know, extended to a very large spectral coverage. And then it merged with continuum, right? So we wanna take the entire H alpha profile, and then we wanna cut that, and we wanna transfer that to a subfolder. That's gonna be named TW, right? H alpha, something like that. And then in that subfolder, you're going to have all the pieces of spectra, right? Probably in my ideal, not ideal, but IDL analysis, if I were doing that, I would create saved files that identify which star that is, let's say star 92, and I would in it put all the information that I have with respect to that H alpha. Why is that? Well, because later on we're going to go to a different level, and that is to do observation. So once you cut, so you cut and you have something like this, right? And as I mentioned, this level here is 0.0, let's say 17. I don't know. I'm making up this number. So, and that thing extends very far away, right? Or go like this and falls down, right? It doesn't matter. So what you're going to do is what astronomers call normalization. You're going to fit a continuum. You're going to normalize the spectra around H alpha. So how do we do that? Well, there are techniques, and I'm pretty sure Python has subroutines that allows you to do. You can do either automatically. You select a window that is, you say, okay, that's pretty much flat. And then you can take an average of that window, right? And then the software automatically take points and then do a SP-line or a regression curve passing through these points. So here is your model for the continuum, And then what you do, you divide spectra by the model. And when this is done, what you ended up with, instead of having a curved spectra like that, you have something that is pretty much set at 1 and go like this, 1, 1, 1, 1, 1, and then you have your line going up and then go down, and then you have 1, 1, 1, pretty much flat on 1. You can have some thing, but it's pretty much flat, and this is 1, okay? Which means you create a model for that. Even if you have parts of the spectra, if you have part of the spectra that is like this, right? So it's a bad spectra, and then you have your H alpha that goes like that, right? And you continue like that. Why it went down, I don't know, some problems, some bogus with the reduction, and here's your H alpha. Then you go to do your continuum normalization. And for instance, I had students that were doing this job, and I told them to do manually. and it was a lot of work. So what they do, they manually would say, okay, this is a continuum, this looks like a continuum, I don't have line here. This is a continuum, this is H alpha in absorption right here. This is an absorption in H alpha, so the continuum should go through here, and it's kind of a visual thing. And then this point should be continuum, should be continuum, should be continuum. And then what they did next is to pass a polynomial, could be a straight line, and if the spectral coverage is small, a straight line would do it, but it could make a quadratic, whatever. And here's my model in red, my continuum model in red. And then once you divide the observation by the continuum, then you ended up with your normalized spectra, and ready for publication, right? So you go like this, and then here H alpha goes in absorption, and then you have a heck of emission. Oops. And then it goes down, and then continue here, it becomes pretty much 1 again. Okay. Now, once you do this cleaning, and I call this cleaning, when you clean the profile of all this 9-2 H alpha emission that way, and see, now you can kind of think about the work that is ahead of you. It's a lot of work. That's why these astronomers, professors, high-ranked professors, they need to have a lot of students and postdocs, because this work is done primarily by students. They learn, and they get to find easier ways to do this, the treatment, and they might develop software that might improve the data analysis. But basically, once this is done, then you can do the same movie, the same one we did, but instead of just getting the FITS file with raw reduced observations, you do a movie using this clean profiles. And sometimes I'm not even mentioning that some, I don't know if you noticed, but some observations, they have spikes, and these spikes are cosmic rays that were not taken during the data reduction. And you have to go there if your intention is to present this data in some professional audience. You have to zap this thing. You have to clean it up. You have to do a lot of cleaning in your spec without changing or introducing information in it. You just need to clean it up a little bit. Okay, so this is the professional normalization. Instead of just dividing by one number or something, or by the maximum, we find the continuum, we fit a polynomial in the continuum, and then we do normalization. This goes in without saying. When we go to determine veiling, right? We need to have all the absorption lines of interest normalized at 1, because then we can compare with our template. So our template, and I have to work on the instructions for that, but our template has to be matching the continuum, right? The continuum has to match, so that we can. So this is in red is my template, so that we can play around and do the veiling the way we know we should do. Okay. Okay. Thank you.